Good morning, everyone. Hi. Um, yeah, I think most of you guys have your real name displayed. I do see a name called Cash Money. Um, please use your name that I can recognize, okay? Because I don't know who's Cash Money when I take attendance. All right, let me just wait another 20 or 30 seconds for everyone to jump in online before we get started. All right. I think we are going to get started, and so the rest may be joining us in just a couple of minutes. Okay. So I would like to just start with a couple reminders here. So exam one is going to be taking place this week. So for you guys sign up for the in seat of sign up for Wednesday's lab section, you are going to take exam one on Wednesday, okay, during the lecture time. And then for those of you sign up for Friday's lab section, you are going to take exam one on Friday during lecture time. Just keep in mind that these two exams are different from each other, okay? So if you ask your Wednesday's classmate for the exam information, it's not going to be on the Friday's exam, okay? Um, so if you are planning to take your exam one in the test center, you need to make appointment with them earlier, okay? And then also you have to let me know so I can send your exam over, right? Otherwise you'll be just getting there and then without exam to take, okay? So that's on exam one. Um, so because I will be in classroom during Friday and Wednesday lecture time to give the exam, so I will not be giving lectures during that time for the other groups of the class. So, but for Fridays, folks, you want to watch the lecture that I will record later on and then post it on Moodle, okay, for the next lecture. And then on Wednesday's lecture, group, you want to watch the video, again, will be on Moodle on your Friday lecture time, okay? So that's for the lecture part. Also for the lab this week, because this week we are going to just practicing some data analysis by using Microsoft Excel. So you are not having any hands-on data taking in the lab. So we are going to do this just remotely, okay? I'll post the Zoom link on the Moodle site on the lecture, under the lecture page, okay? But so I think what I'm going to do is I'm going to record the introduction part and then post also on Moodle so you guys can watch them separately. So during the lab time, I'll be online on the Zoom, and then you guys are also join the lab on via Zoom. But I'm going to make breakout rooms for you guys to work as groups. Okay, so you guys can watch the video along the way, and then to see what will be what you guys will be doing in the lab. Okay. So the video is going to be just brief video, but you can check the lab manual, okay, to see what you are going to do in the lab. So as I said, the lab manual is very precisely written, so everything you will need will be in the lab manual as well. Okay, so these are the what we are going to do for this week. Okay, so anyone has any questions you might have? All right. Also again, so um, there's one of you guys put your name as Cash Money. So I would like you to change your name or let me know who you are, because then I wouldn't be able to take attendance for you if your name is Cash Money, because I have nobody whose name is Cash Money on my roster. Okay. All right, so we'll get started with the lecture part. Again, we'll be just looking at what we talked earlier last time. So last time we start chapter 4. We formally introduced the definition for force. So it's either a push or pull. It's a vector quantity. So when you describe the force, you want to give the magnitude and also direction of it. Okay. And then I think we talked about free body diagram. So free body diagram is simply you draw all the forces on your object of interest, okay, all the external forces. And then for your object of interest, you can represent it with a dot, okay. We also talk about Newton's first law of motion, or Newton's law of inertia. So basically it says unless there's a net force on the object, its velocity will not change. Okay, so it will be either stay at rest or keep its original velocity, right? Unless there's net force. Now, if there's net force, then the velocity will be changing. So today we'll be looking at Newton's second law of motion. Um, so this is the figure shows here as a demonstration lab. Okay, so if you pull an object with a force F1, all right. So in this case, there's a block over here, and then this track over here is air cushioned track. So then the friction is negligible compared to the force that you apply F1. Okay. So then you can measure what's the acceleration under the influence of F1. Now, if you increase your F1 by 2 times, becomes F2, you can also measure the acceleration due to the second force, twice of F1. Then you'll figure out that the acceleration is going to be twice of the original acceleration. Okay, so if you would do this in the lab, you will figure out that the acceleration the object is having is proportional to the force applied to it. Okay, so you can do it this way. Then that tells you A is proportional to F. You can actually, from your daily experience, you can conclude that. So for example, if you push a lighter, say basketball, with the force F, okay, and then at the same time, if you are pushing a heavier object like a car with the same force F, then you'll figure that the basketball will probably have larger acceleration than the car, right? Because the basketball, then its velocity will be changed more dramatically than the car. So in that case, you can conclude that the acceleration it's inversely proportional to the mass of the object. Okay, so in this case, the smaller mass object will gain larger acceleration, larger mass object will gain smaller acceleration. Okay, so combine these two in piece of information, then you can arrive at this expression over here. So acceleration A is proportional to F, but inversely proportional to the mass. Okay, so you can write up this equation A. It's probably going to be equal to F over M. Okay, so this is basically Newton's second law of motion. All right, acceleration of the object is proportional to the net force, and then inverse proportional to the mass. Or you can rearrange this equation, the first equation, so then you'll have F equal to M times A. Okay, so I think this is more often you see Newton's second law express an equation. So F equal to mass times acceleration. That's the second law. Force, or to be more precisely, we should say net force is equal to mass times acceleration. Okay. All right. Now, because force is a vector, all right, and then acceleration is also a vector, so it's more concise to write in vector form. So force with an arrow that indicate it's a um, vector form, and then mass times acceleration with an arrow, as that's also a vector, okay? And with a summation over here, sign in front of the force, that indicates you are summing all the external forces on the object. So then this gives you net force, okay? So this sign tells you this is net force, okay? So net force is equal to mass times acceleration. All right. Now for force, the SI unit for force is going to be newtons, all right, because it comes from this equation. You can see it's equal to kilogram from mass times acceleration of meters per second square. Okay, so it should be equal to 1 kilogram. The force is in SI unit of kilograms times meters per second square. All right, now because this is a new quantity here, so we usually introduce a new unit for it. So in this case, we will give it Newton to honor Newton, who discovered Newton's laws of motion. Okay, so this is in newtons, all right? But you should be keep in mind that Newton is equivalent to kilograms times meters per second square, all right? A couple of other units you might be seeing that when people write force, um, dying sometimes it's assigned to force. So that is using CGS units, means centigram, centimeter, gram, and second units. Okay, so the basic dimension here in this unit system is centimeter, grams, and second. Okay, so grams is the mass, the unit for mass, and then centimeter per second square is the unit for acceleration. All right, and then if I under that unit system, dying is the unit for the force. Also, British unit, we will not see it so often in this class, but in British units, the mass is having a unit of slug, and then acceleration is in foot per second square. All right, force, in that case, force is in pounds. Okay. All right. Um, so So this is Newton's second law. Basically, it says net force equal to m times acceleration. Okay, so let's take a look one example here. Newton's law and kinematics. Okay, so we have just learned Newton's law. Now we are going to see how you can apply Newton's law on top of the kinematics we learned in the previous two chapters. Okay, so I will give you guys a maybe just 1 or 2 minutes to understand the problem and then get started, and maybe having a plan how you want to solve all this. But we will look at this solution, the solutions for this one together in a couple of minutes. Okay. All right, so let's get started. First, let me stop sharing so you guys can see the um, my screen here better. On my yeah, my pages here better. Okay, so we'll first start just sketch the problem here. So there's a 92 kilogram water skier floating in a lake. Okay, so the mass include the water skier, the person, and then the ball here, the skier here. So the mass is given as 92.0 kilogram, and then it says it's pulled from rest to a speed of 12, okay, meters per second, 12.0. So this is the final speed, and then over a distance of 25 meters, okay. So also it says from rest, so that means initial speed is 0, okay. It's asking what would be the net force exert on the skier? Okay, so then this is the net force. Okay, so there's probably a pulling force. There's also like resistant force from the water. But if you just look at the net force, then you'll be just looking at the net force. Okay, so it will be the pulling force minus the resistant force, which both are included in this net force expression. So it's looking for this net force. Okay. Now we just learned Newton's second law, right? Second law says net force is equal to mass times acceleration, right? So then we are looking for net force. We need to know the mass, which is given. The acceleration is not, right? So then how do we figure out acceleration? So because the water skier is moving in just one direction over here, okay? So we are going to assume this is just one directional motion and then constant acceleration. So then 1D constant acceleration, constant A, all right? Then you'll realize, okay, so then this is Newton's second law. We apply here, and then now we need acceleration. So we probably want to figure out the acceleration from one-dimensional constant acceleration motion, right? So for that, we learn 5 equations of motions, right? So x equals to x naught plus v average times t, and then v average is equal to 1/2 of initial plus final, okay? And then the third one is v is equal to v0 plus at. All right, the next one is x equal to x naught plus v0t plus 1/2 at squared. Okay, the last equation is v squared equal to v0 squared plus 2a times x minus x naught. All right. So in this problem here, d, the distance that is the skier have traveled, that's from like x naught to x, right? So d then is equal to x minus x naught, right? So that's equal to 25. All right. So then if you look at the equation of motions here, you are looking for acceleration that is you needed in the Newton's second law over here. So you'll be looking at through these equations to see which one you'll pick for to solve for your acceleration. Okay. So I'll give you guys a few seconds to think which one you want to pick. So it looks like we are not going to pick the first one, right? Because the first one doesn't have acceleration in it. We are not going to pick the second one. Second one doesn't have acceleration in it. Now the third one, can we pick the third one? It has, the problem gives us the final initial, right? But it doesn't tell us the time t. So it looks like we are not going to take the third one, right? Because we don't know t. And then similarly here in the fourth equation, there's t there, there's also acceleration. So you're probably not going to take the fourth equation, all right? Now let's look at the last equation here. We have final, we have initial, we have x minus x naught, which is distance travel. So we can use the last one, the fifth one, okay? So it looks like we can use the fifth one. Let's use that one then. So we'll be doing v squared equal to v0 squared plus 2a times x minus x naught, which is d, okay? I'm going to just say d, all right? So then I'll be figuring out my a, all right? So you're going to subtract v naught from both sides, So then V square minus V naught square equals to 2A times D. Now you are looking for oscillation, so divide both sides by 2D. That will give you your oscillation. Okay, so oscillation is going to be V square minus V0 square divided by 2D. And it's going to be 12.0 meters per second square minus 0 square divided by 2 times 25 meters. Okay, so this will give you, let me see. This is going to give you 2.88 meters per second square. Okay, so it's 2.88 meters per second square. Okay, so this is your oscillation. All right, now you have found your oscillation. You can take your oscillation into Newton's second law to figure out your net force. Okay, so then your net force, summation of force. So this sign, it's summation sign of force is equal to mass times oscillation, 92 kilogram times 2.88 meters per second square. Okay, kilogram times meters per second square, that will give you newtons. Okay, so this tells you it's going to be about 264.96 newtons, which you keep 3 6 fixed. It's going to be 265 newtons. Okay, any questions you guys might have? You can unmute yourself and then speak up. Okay, all right. So if no questions, then let's take a look on. Okay, let's take a look on a second example here. Okay, so it says in a grocery store, you push a 15.4 kilogram shopping cart horizontally with a force of 13.4 newtons. Now ignore the friction force. If the cart starts at rest, how far does it move in 2.5 seconds? Okay, so in this case, you are looking for distance d. All right. So on this one, I'm going to break you guys into breakout rooms, and then you can kind of discuss on how to solve for this one. Okay, and then I'll give you guys let me see, about maybe 5 to 8 minutes on this. Okay, and then I will close the breakout rooms at the end of that time period. So let me assign you guys to the breakout rooms. All right. Hi guys.
Hello. So I missed the question. I didn't have um, the slides open, so I have to go look at that real quick.
Okay, yeah. Yeah, I want to find out who it actually cashed money because I'm quite interested.
I have no idea. I heard you that. Do not believe that that's what my name is.
That's not, yeah. You have your name displayed correctly. All right. I'm going to type the question in the chat here so you can refer to that.
Thank you.
All right. Yeah, I will leave you guys here. Okay. I'm going back to the main room. I'll see you later.
All right. Thank you.
Mhm.
Yeah, I used. Yeah, I think that's the one I used. I just rearranged it for. Yeah, sorry, my other stuff.
All right.
I ended up getting 2.72. Not sure if that's right or not.
What's
I didn't realize I was muted. Hey, guys. Yeah, that sounds right. 2.72.
Okay.
All right, just wanted to check if you guys have any questions. All right, I will
Nothing.
see you guys later.
Can I ask a question?
Oh yeah, go ahead.
I'm still struggling with how to get the equation because I thought it was the x equals x0 plus v0 t plus 1/2 at squared, but like
Mm-hmm.
I'm not. I guess I'm not getting the time either. So
Yeah, time is 2.5. It's stated in the problem, so you need to figure out the acceleration first, using Newton's second law of
yeah,
motion.
I did that and found that.
Okay, great. So time is
But
2.5 seconds.
oh, okay.
Yeah, it's there. Yeah, it's in the problem.
That's not 2.5 meters per second. It's just 2.5 seconds.
Yeah, it's 2.5 seconds.
Oh, I messed it up.
Yeah.
Okay.
Okay. All right. Looks good. I will see you guys in the main room.
Okay. Bye.
Bye bye.
Dr. Ho, I have a
Yes.
quick question regarding the exam.
Sure.
I was wondering, so will we have an equations sheet for the exam? Does that make sense?
Yes, I will give you guys during the exam a sheet of equations. So there's will be a equation sheet to be given. So it's going to be just including base equations like equation of motions, one-dimensional, two-dimensional, and then probably like components of vectors, etc. Okay. So so you will start with the base equations. Okay. Just I will not give you like a final equation to use to plug in numbers and then calculate that. Okay. So you'll be giving just basic equations. Okay. All right.
Can I double check with the answer? Or are you just going to go over it?
Okay, so you probably kind of join in later. So the question was if a sheet of equation will be given during the exam. So yes, I will give you guys basic equations like equation of motions for one-dimensional, two-dimensional, projectile motion, etc. And then like components of vectors should be vector times cosine for x and sine for y, etc. Okay, so those types of equations will be given. All right. Okay. Let me know if you still have other questions about it, about the exam. All right. So if not, then we'll take a look on the solutions here together. All right. So I probably have announced this earlier, but I was kind of jumping in between breakout rooms to see if you guys need help. Okay. So so from now on, if we are holding breakout room discussions, expect that I might be popping in at some time. Okay. Or at any time to ask if you have questions. So let's take a look on this one here. So it says in a grocery store, you push your shopping cart, right? So let's do a sketch here. So you guys probably realize that you don't have to be a good drawer. Just maybe kind of illustrating on. So this is the force you are pushing on. All right, so the cart, it says you push on the cart for t equal to 2.5 seconds. All right, the mass of the cart is 15.4 kilograms. The acceleration is not given here, but it says the force you are pushing on is 13.4 newtons. It's asking you how far does the cart move in this 2.5 seconds. Okay, so this distance, all right? Or if you want, you can say x minus x naught to be the distance, okay? X minus x naught. Or taking this as initial 0, then you'll be just looking for x, right? So this is initially 0, then you're looking for x will be the distance, all right? So again, because we just the Newton's second law, so you probably might realize you probably want to use Newton's second law here, this equation, in addition to the 5 equation of motions here. So you're looking for x, right? So for the first one here, again, we are going to just check through these equations of motion. So the first one here, it doesn't give you any information about the velocity, the speed, right? Initial or final. So you probably, again, don't want to use that one. And then also this one doesn't have x on it, in it. So the third one doesn't have x in it. So you probably won't use that one either. The fourth one here, you'll realize, okay, so you have x naught as 0, v 0 naught, that should be 0, okay, to start with, because when you just push it, then it's going to be from rest, okay? So I take that back. So on here, you are not given final, so you couldn't figure out the average here. You do have the v naught, but you don't have final, okay? So you are given t, all right? So you probably need a acceleration here. You're not given acceleration, right? But because we just learned Newton's second law, you may be looking at, take a quick look on the Newton's second law here and then see if you can figure out the acceleration quickly here. So it tells you your pushing force is 13.4, and it also tells you ignore the friction force. Then this force will be the pushing force will be your net force, okay? Should be equal to 13.4 Newtons. With that, then you can, by Newton's second law, you can solve for your acceleration. So 13.4 Newtons divided by 15.4 kilograms, okay? So you'll get 0.8701 meters per second as your acceleration. Then you can plug it into the force equation among the equation of motions here, okay? So then x equal to x naught plus v naught t plus 1/2 at squared. So 0 on the first turn, 0 on the second turn, and then you'll be just doing 1/2 acceleration times t squared, okay? 2.50 seconds squared, okay? So this will gives you about 2.72 meters, okay? So a little bit less than 3 meters, okay? So you can kind of imagine that if you are in a grocery store, if you push your car for about 2.5 seconds, like between 2 and 3 seconds. So that's probably about the distance you will travel, okay? So about 2 to 3 meters then, okay? So your answer kind of looks, makes sense on that check there, okay? Any questions you guys might have on this one? All right. So if you are clear, then we can move on. The next section here in the textbook talks about Newton's third law of motion. Okay, so it's basically about symmetrics in forces. Okay, so for example, if you are pushing on something, okay, for example, if you are pushing on a heavy couch, or you are pushing on the wall, so when you are giving the force to the wall or to the couch, okay, at the same time, you feel like the wall or the couch is pushing back on you, right? So this is basically Newton's third law of motion. So it says if there's a force acting on an object, okay, then at the same time the object will be exerting the force on the object that is pushing on it. Okay, so if you push the wall, then the wall is pushing back on you. Okay. So for the two forces, the force you're pushing on the wall and then the force that the wall pushing back on you, they are having the same magnitude, but in the opposite directions, okay? So in the case, in the figure shows here, if you go swimming, you start pushing on the wall here of the pool, then the wall is pushing back on you on your feet over here, okay? So if you push, say, 20 newtons of force on the wall, then wall will be pushing back on you with 20 newtons of force, okay? Now realize, so for this is Newton's third law of motion. So these two forces, okay, the one on you, the one on the wall, they are called action and reaction forces, okay? So because there's action on the wall and then the wall will react back, okay? So action and reaction pair. There's a couple key features here. So one is these two forces are having the same magnitude, okay? And second one is these two forces are in opposite direction, all right? Now the third feature of this pair of forces, they act on different object, okay? So one is acting on your feet and then the other is acting on the wall, okay? So they have to act on the different object, okay? Otherwise they are not action and reaction pair, okay? All right, so basically Newton's third law of motion says forces always come in pairs. If you see one force, then you will find another force that is its pair or its reaction force, all right? And then these forces are called action and reaction forces, okay? And again, they are acting on different objects, Another example here, if say a professor is pushing on a cart with equipment, so then let's look at this here. So the pushing force by the professor here is on the cart, and then the cart is first pushing back on her here. Okay, so then these are a pair of action and reaction forces. All right. Now also, as she's walking on the floor here, so then she's pushing back on the floor. Okay, and then the floor then is pushing back on her foot here, backward, or forward in the forward direction. So then this, the force by the foot on the floor, and then the force by the floor on the foot here, they are pair of action and reaction forces. Okay, so these two, this is one pair of action and reaction forces. This is another pair of action and reaction forces. Okay. Now another examples over here. So on this guy here, okay, so in this case, if you are holding a bag here, all right, so then your hand is exerting on a force upward, supporting force. Now at the same time, the bag itself, due to gravity, has a gravitational force on it. Okay, so these two forces, they are opposite in direction, right? They are the same in magnitude, but they are not an action and reaction pair forces because these two forces are acting on the same object over here. Okay, so then this case, this is not a pair of action and reaction forces because they are acting on the same object. Okay. Also on here, if the bag is placed on the table here, the normal force by the table, which is a supporting force, so it gets the name of normal force is because it's pointing on along the normal direction. Okay, we'll talk about this later. But there's a normal force over here. There's a weight here. So this, again, these two are not pair of action and reaction forces because they are acting on the same bag here. Okay, for a pair of forces to be action and reaction forces, they have to act on different objects. Okay. All right. So let me see. Yeah, I think we have about 13 minutes remaining here. Maybe not quite enough to solve for this one, but I'll stop the lecture here for today. If you guys have any questions, again, about exam one, or if you have some questions on understanding some of the problems in homework 1 through 3, I will remain online here for the remainder of the class. You guys can ask me questions in preparation of the exam, okay? Otherwise, if you are good to go, then you can leave, okay?
Can I ask something real quick?
Yes.
So, for the test, you said, I don't know if you said anything about a study guide. I thought you just said to look over the homework problems. I know that, but I thought I heard something about that. So,
Yeah, that's right. So make sure if you can solve all the problems by yourself, then you should be good.
okay.
All right. All right. Anyone of you guys have any questions regarding exam 1 or anything else? If not, I'm going to end the meeting for today. Okay. See you guys.